Okay, I think we will start. It's time, and welcome to Chandra Data Science workshop. This is session 8, and we'll have 2 invited talks and contributed talk and 5 minutes lightning talks in this session. And we'll start with the invited talk by Antoine Meyer from Imperial College London. Antoine is a student in statistics working under supervision of David Van Dyke, and he will present his work on eBASCS, which is, I should mention, this work was recognized by American Statistical Association at the JSM meeting as one of the nominated work by a student in statistics or astrostatistics. We'll start, Antoine, and go ahead. I will give you some warnings, but congratulations for the nomination of the student paper competition.
Thank you very much, Anita. I'll share my screen right now. Please let me know when you can see it.
I can see it, yes.
Perfect, thank you very much. Thank you very much for inviting me to present my research. This is actually my first ever invited talk, so I'm very grateful for the opportunity. So as you said, I study at Imperial College. I'm a second-year PhD student, and today I will present my work on eBASCS, which is an algorithm designed to sift high-energy photon events from multiple sources with overlapping point spread functions. So before starting, oops, I'm sorry, I don't seem to be able to. Oh God. I'm really sorry about this. Now I can switch. Okay, great. So yeah, before starting, I would like to quickly advertise the paper presenting eBASCS and that we recently published in MRAS, and give a huge thanks to all my co-authors, David, Vinay, Lewis, David Jones, Anita, and Andreas for their help and support on the research. So here is the link to the paper if you want to check it out. And I should also mention that this work is a direct extension of the method that was designed by David Jones in 2015, a method called BASCS that some of you may already be familiar with. So what is the problem? So we're interested in the analysis of individual X-ray sources that appear in multiple systems or in crowded fields. And in this setting, conducting a meaningful analysis relies on your ability to identify the sources that are emitting photons on your observation and the allocation of those events to the sources, so you can study the individual sources in isolation and free of contamination from the other components of the system. The problem is when you're observing clusters of contiguous sources that are very close together, well, there may be an overlap in their point spread function, which causes uncertainty on the origin of the recorded events and also on the physical, spectral, and temporal properties of the system components. And I should note that this uncertainty is often amplified by common issues in X-ray data, such as low count data and high background contamination. So I'm assuming that everyone here knows what the point spread function is here, but just in case, the point spread function is the response of the imaging system to the incident photons that redistributes them on the surface of the detector according to a distribution that is centered on the location of the source. So as you can see on this example here for the binary system HPC 515A that was observed by Chandra, well, you have those two sources that are very close together, and because of the PSF, well, you have those clusters of photons that intersect, and it is clear that in the intersecting region of these PSFs, well, it's quite uncertain where the photons originated from either of those two components or the background. So usually the way to go around solving this problem is by manual extraction, meaning that you would define source and background extraction regions for the source region. So you define a region around the core of the source, and maybe in other regions, such as in the source's wings that are away from the overlapping region. The problem with that is, well, the core of one source is very likely to be contaminated with photon events from the other source when they're close together. And so what you have is a sample of photons that are supposed to represent one source, but actually contains events from the other source. And then your analysis will be subject to error and uncertainty. And this uncertainty is also going to be inflated by the fact that you're effectively discarding all of the photons that do not fall in one of your extraction regions. So you're already quite in low count setting in X-ray data, and you're discarding some valuable information. So your analysis will be all the more uncertain. And another problem is that that yields a deterministic allocation. And this is problematic because you're introducing a lot of uncertainty with the source separation strategy that are not taken into account in your allocations and analysis. So this is why we're interested in more algorithmic and probabilistic methodologies that can really take into account this uncertainty. And this is where we're coming from with eBASCS. So our method eBASCS is able to probabilistically allocate recorded photon events to observed sources, meaning that the output of our algorithm, instead of being just one allocation, gives for each observed event a probability that that event belongs to one of the sources or the background in the observation. eBASCS is also able to compute source parameters of interest, such as location, relative brightness, background contamination, and all of that while taking into account the uncertainties in your photon allocations. eBASCS is also able to leverage the spatial, spectral, and temporal information to perform a refined disentanglement. So as I said before, our method is a direct extension of BASCS, the method designed by Jones et al. In 2015. And BASCS was only considering the spatial and spectral information, and we're extending that to incorporate the temporal dimension because we're interested in tackling the problem of overlapping sources in the case of time variable sources. So astronomical sources may display some brightness and spectral variability, and if you can somehow leverage that information, well, you can somehow improve on your on how you differentiate between sources in a system, and hopefully you can get a better allocation of events to the sources by leveraging this information. And as a motivating example, here are the light curves for a binary system UV set T, and one of the components UV set P dramatically flares during the observation period, and in this case it's quite logical then taking into account this temporal information will be very helpful to separate between the two sources. So now that we set the stage, we can dive into the statistics. So X-ray data is typically acquired as event lists. So the detectors will record detector spatial coordinates xi and yi, photon event arrival time ti, and photon energy ei. And so now we'll make an initial batch of assumptions around which we can build a model for this data. So we'll assume that each event originates either from the source, from sources in the optical field of view of the detector or the background. We will only consider point sources. We'll assume that the number of sources is known in the observation. And we assume that the locations, intensity, spectral distributions, and light curves are unknown, and we'll try to learn about them. So essentially what you have is some data that is assumed to originate from a collection of subpopulations, and each of these subpopulations represents either some sources in the observation or the background. And in this setting, it's a natural way of modeling this type of data is via a finite mixture model. So essentially what you're saying is each photon event xi can arise from either from some component distributions that will represent either the sources or the background. And in this case, the likelihood of your data, so the probability of observing your data given your model, is, as a consequence of the law of total probability, just the weighted sum of this component distributions that represent source of background, and the weights in your weighted sum, the mixture weights, will give the proportion of the population, so of your photons that originate from mixture component J, so source J. And in an astrophysics context, this W can be interpreted as the relative intensity of source J in the observation. So we're interested in learning really which mixture component underlies each event that we observe. So for that matter, we introduce latent indicator variables SI, where SI equals J if photon XI originates from source J. So now that we have this framework for our model, we need to construct models for those HJ's distribution for the individual mixture distributions. And because we have spatial, spectral, and temporal data at hand, well, each of those distributions will be a combination of submodels for the spatial, spectral, and temporal data. So starting with the spatial data, so as we said before, the detector coordinates, the recorded detector coordinates for a photon are a deviation from the true and unknown location from the event's originating source. And this deviation is induced by the PSF, which is detector and telescope specific distribution centered at this unknown location that would denote mu J. So this yields the following distribution that I wrote here in the box. And so in our case, we use an analytical PSF, which means that we can evaluate it with a closed form formula. And in particular, in our numerical studies, we use the King profile density. We also assume that the background is uniformly distributed across the image. And we expect that this assumption of spatial uniformity for background events, that our model will be quite robust to this assumption because photons that are spatially distant from the sources will be allocated to the background irrespective of the background model. So onto the spectral data. So here our strategy is to approximate the observed spectral energy distribution and not the actual source spectra with a rough shape so we can exploit spectral differences among the sources. So what that means is we're ignoring the effects of the redistribution matrix function and the auxiliary response file. And this is because approximating the spectra with a rough shape can help us really differentiate between the sources without a lot of added computation. So for this rough approximation, we use a gamma distribution. Reason for that is it's quite simple. It has positive support and has its mode in the mid to low energy region, which makes it suitable. And in some cases that you can see on the picture on the left, a single gamma distribution might not be quite flexible enough to capture the spectra of the sources. So in this case, you can use a mixture of gammas to be more flexible. And this is just a weighted sum of gamma distributions, 2 gammas or more if you want. And same assumption as for the spatial data, we assume that the background is uniform in the energy dimension. Now on the temporal data, our strategy is similar than with the energy data. So we're not trying to learn the spectra or the light curve in a detailed science-based manner, but rather want to extract shapes and trends that will help us differentiate between the sources in the system in an easy way. So for that matter, the model that we use for the light curves is just a piecewise constant function on a pre-selected collection of time bins that segment the observation period. So how we do that, so first of all, we have to cut our observation period into time bins. And to do that, we developed a simple data-driven procedure that finds the time locations in the observation that best isolates the transient variations and flares in the observed light curve of the system. And using these locations, we can define the time bins. And once we've defined those time bins, then what we do next is discretize time. So we define this variable bi, where photon I falls, so bi equals k if photon I falls in time bin number k, say. And because we're saying that our light years are constant on these time bins, well, the relative intensity of a given source on the time bin is just going to be a constant that we call lambda jk if it's source j and time bin k. And so the probability that a photon from source j falls into time bin number k is just lambda jk, which yields the following model for photons originating from source j as following a categorical distribution, where the probabilities of falling into each bin are given by the lambdas that sum to 1. We also developed, theorized a model to allow for the energy distribution to be time variable, meaning that we can fit a different spectra at each time bin. For example, using one of the models that we defined earlier, like a gamma distribution or a mixture of gammas. So that's in theory, but in practice, well, in each time bin you have a limited number of data. And so it might be that you don't have enough data in those time bins to estimate your parameters with useful uncertainty intervals. And so because this spectrum model, the number of parameters will grow rapidly with the number of time bins and the number of sources that you consider. And so it's quite difficult to fit. So in our numerical studies, we just assumed that the energy distributions were constant during the observation, but that's a possibility. So now that we defined the models for the spatial and temporal data, well, we can combine those models into the likelihood for the whole data. And we assume that the spatial, and temporal data are independent conditionally on the assignment assignment variable SI. So a condition on that, your likelihood is just going to be the product of your individual models for the 3 different types of data. And we can also consider models with different combinations of this different submodels. So in our analysis, usually our baseline model is just the spatial model, so a model that only uses the spatial information. The eBASCS method by Jones 2015 was spatial plus spectral. And in some cases, the detectors do not record the photon energy with useful accuracy. And so we can use the spatial and temporal combination in that case. So now we need to learn about those parameter values. So we choose to operate within the Bayesian paradigm because it allows us to quantify the uncertainty of the model parameters via their joint posterior distribution given the observed data. So once you have your likelihood that we defined earlier, you can have prior distributions that you can use that represent your prior beliefs about the parameter models, model parameters before seeing your data. And you can use those to incorporate scientific knowledge about the likely values of the parameters. So for example, if you have an idea of where one source is, well, for the parameter that encodes the location of that source, you can just set a normal prior centered on this location that you think is very likely to be the case. And so Bayes' rule gives the expression for the posterior distribution, the updated beliefs of your parameters after seeing your data. We ourselves just use computationally practical pairs usually, so conjugate distributions, and we sample from the joint posterior distribution of our model parameters and event assignment variable S via Markov chain Monte Carlo sampler, in particular the Metropolis algorithm. So to see to what extent eBASCS is able to outperform other algorithms such as spatial and BASCS in the case where the sources display variability in time, we designed a comprehensive simulation study that you can find in the paper. And here I'd just like to focus on one specific example. So we have 2 sources, a bright one, the blue source, and a faint one, the red source, where the bright one is approximately 10 times more intense and than the red source, faint source. And our faint source is completely overwhelmed by the background in this case. It's 5 times more intense than the faint source. And we're trying to see here to what extent eBASCS is better at computing model parameters of interest, such as the location of the sources. So under the simulation setting, we simulated replicate data sets. And for each of those, we're computing the posterior mean, which are the dots in the images, and the standard deviations, the ellipses, for the source locations. And you can see that eBASCS is much better at finding the location of faint source, even though it's completely overwhelmed by the background, because it can leverage this temporal information that the others cannot, and use that to improve and have better allocation and estimate the model parameters more accurately, more consistently, and more confidently. So now what happens when we apply that to a real data set? So we're studying UV-Set. It's a binary system observed by Chandra with the LATGS plus HRCS configuration. And so this data set was already analyzed before using very small extraction radii around the sources course to limit the contamination. And you can see that even though the sources are well separated, well, because one of the sources, UV-Set B, undergoes a very large and dramatic flare during the observation period, this flare still contaminates the light curve of UV-Set A, as you can see on the right. And this is why this example is a good test for eBASCS. And we'll see just right now that eBASCS can provide a more careful allocation of the events and remove the contamination of the flare of UV-Set B on UV-Set A. So because the LATGS plus HRCS configuration does not record the event energy with useful accuracy, in this case, we use the space plus time model. So we're not using any spectral information in this analysis. And so to compare the different models, what we do is we conduct an analysis that we call the disputed event analysis, which is basically we're performing allocations of photons to sources using our spatial model, the baseline model, and our space-time model. And we're looking specifically at the photons whose allocation changed when we incorporated the temporal information in the model. So as you can see on the image, the photons that were disputed among the algorithms were mainly in a region equidistant from the source's cores, which is, of course, going to be the most difficult one. Photons in this area are going to be very difficult to separate using spatial information, of course. And when you look at the grid events, especially, which are the events that were allocated to UV-Set A on the right by the spatial only model, and that were moved to UV-Set B by the spacetime model, well, they have to be allocated to UV-Set B based on temporal information because they're circling the core of UV-Set A. And this is what you can see here in these plots on the right. All these events that were moved from UV-Set A to UV-Set B when adding the temporal information, where they were all detected at a time that is coincident with UV-Set B's flare. So those are the green bars in this plot. And so this contamination from UV-Set B and UV-Set A is now removed by eBASCS because, or the spacetime model, because as you can see, the light curve as allocated by spacetime of UV-Set A does not contain the spike of intensity during UV-Set B's flare at this moment. So, and same for the other way around. The contamination of UV-Set A on UV-Set B at early times in the observation period from 0 to 15 kiloseconds is also removed by spacetime, the spacetime model, and reallocated to UV-Set A, as you can see in this plot. So so this is where eBASCS is at right now, and there is a number of extensions that we would like to work on and that we're currently working on. And so first of all, on the methodological extensions, we'd like to replace the step function temporal approach by simple time series model because the step function, I guess that's
2
my
minutes.
time.
Yeah,
Okay.
2 minutes, yes. It's going.
Thank you.
Yeah. No.
Yeah, the step function approach, you can make it very flexible by considering a very high number of time bits, but of course this is not very scalable because you'll have a lot of parameters to fit. And also we have the added burden of defining the time bins before using our model. And all of these problems are kind of removed if we use simple time series models. So we're going to experiment in that. And we also want to extend our spectral modeling to account for the RMF and the ARF. And perhaps the most important one, we want to allow the number of sources to be an unknown model parameter to fit. So This was one of the features in eBASCS 2015, and that is our next move. And this will require a more sophisticated algorithm, reversible jump Markov chain Monte Carlo. And on the astrophysics side, we'd like to extend our spectral modeling to grazing line data, for example, UV set. We studied the 0th order image just before, but if we can separate the grading lines during our algorithm, then we can do a lot of interesting analysis after that. And also, last thing, that it'll be interesting to see whether our algorithm is able to explore observations produced by detectors with very low spatial resolution, such as NuSTAR, and if it's able to separate components using a more advanced spectral and temporal modeling. So yeah, this is it for eBASCS, and thank you very much for your attention, and I look forward to your questions.
Thank you, Antoine. Okay, we have time for a few questions, and people can, there are two questions actually. The first one is from Rafael Martinez Galarza. Thanks, Antoine. Would you say that adding the temporal info is mostly useful during clear flaring or dipping situation? And what happens in cases where the two sources have uniform fluxes over time, but different brightness? Does temporal info also helps in this case? So this is, you can see the question in Q&A if you click on it.
Yeah. So yeah, for your first question, it is also useful when you have temporal variability that is not as marked as a flare. For example, in the paper, we include an example studying the HPC 5.5 system, which does not flare, but have just a little bit of temporal variability. And you are able to extract interesting things out of that with less marked temporal variations. And so I remember this. I'm having issues opening the Q&A right now. So could you please remind me of the question?
Yeah, so what happens in cases where the two sources have uniform fluxes over time, but different brightness? So basically you have two sources which, have the same shape.
All right. Well, then whatever you get out of eBASCS would be exactly the same thing as what you get from algorithms that do not use the temporal information, such as eBASCS or the spatial. You will just recover exactly what you get from those algorithms that do not use the temporal information.
Right. And there is a question from Jeff Scargill. Suggestion for time domain models. Bayesian blocks is a non-parametric approach to step function modeling, objective, data adaptive, and only one parameter. So this is for the time domain part.
Right. Yeah. Thank you for the suggestion. Yeah, definitely explore that. Thank you.
Yeah. And one more question from Scholen Ballman. Can you compare your model with the Baymax model for multiple AGN that has been discussed last week? Or are they very different? I see that they do not use RMF.
Right. So my understanding of Baymax is there's a base factor computation to decide whether an observation is either a single or a dual AGN, I think.
Right.
Well, I mean, I don't think you could use, as far as I'm concerned, I don't think you can use, for example, Baymax on multiple systems with more sources, for example, which is something that you can definitely do with eBASCS. And I am not sure that Baymax uses temporal information, but I could be wrong. But so yeah, those are different points between the methods.
Yeah. I guess there is some comparison, and you can look at that these two methods, but they definitely different, I think. Yeah. And then we have one more question from Keith Arnold. That's the last question, and Keith asks, how do you estimate uncertainties? Suppose I'm interested in the count rate. Do you derive a posterior distribution on the count rate?
Right. Yeah. So when you estimate your light curve, for example, then for each step function, so for each step, you'll have like an uncertainty interval on the intensity of the source during this time bin. So this will be your uncertainty estimation on the count rate at this time interval, if that makes sense. Yeah, so a posterior interval around the value for the constant value of the flux at this point.
Right. Okay. I think if there are no more questions in Q&A, but if there are other questions, please go on Slack and ask Antoine. Thank you, Antoine. And we will have the next speaker to share the slides. Maybe stop sharing yours.
Thank you very much.
Yeah, thank you for nice talk. Right. So our next speaker is Vikram Dwarkadas from University of Chicago. And this is a lightning talk. So this will be 5 minutes presentation.
Okay, can you see my slides and hear me?
Yes, yes.
Okay, thank you. Thanks very much. And today I'm going to be talking about SNaX, which is a database of supernova X-ray light curves, and you can find it at this URL. So the first question, I guess, you might ask is, why do we want to plot supernova X-ray light curves? And there are many reasons you can look at these papers that I've mentioned out here. I won't go into too much detail, but the one thing I do want to mention is that suppose that the X-ray emission is thermal. The luminosity then goes as density squared into some cooling function into the volume, which basically means that the luminosity is proportional to density. And if you study the evolution of the luminosity, which is the light curve, you get the evolution of the density into which the supernova is expanding, which means you get the density profile of the surrounding medium. And that density profile can be related to the progenitor star. And that's one of the main reasons for studying the supernova light curve. There are many other things you can learn from there again, and you can look at these papers. So we wanted to study a lot of supernova light curves. And the thing we realized is that, there were many databases which gave you like optical emission from supernovae, but there was almost nothing that gave you the X-ray emission from supernovae. And so we decided that, we'd make a database that gave you the X-ray emission from supernovae. And so that's where SNaX came about. And SNaX was first created by an undergraduate student, Matthias Ross, working with me. And this undergraduate student now doing a PhD at UCLA. We created a searchable database of X-ray light curves with PHP and MySQL and with the Flot graphing library. Again, as I mentioned, you can find it at this URL. And if you want to read up the paper in detail, which we discussed it's in the Astronomical Journal in 2017. So that was when it was first created. It was updated by another undergraduate student, Ali Nisanoff, working with me. This was upgraded to PHP 7 because the machine itself had to be updated, and so did SNaX. And she also improved the security. And we published a research note, which you can see there. And finally, Ali and another student, Daniel Sharkey, combined together to make the whole database accessible to the visually impaired. So currently, SNaX is a fully accessible database, and we would really like you to use it. Oops, sorry. So what happens when you go into SNaX? Well, you get a completely searchable interface. You can search any way you want. You can search by the object name. You can search by the type of supernovae, the galaxy, the flux, the luminosity, the age, almost anything you can dream of. So you can sort of search for it in that manner. You can also look at the data individually. You can the data of each supernovae. You can look at the data of several supernovae. You can select them all. You can select a particular supernova and then look at all the various data underneath it, which is basically the data points, individual data points. And you can see that each of them, has the flux itself and the luminosity given a distance. And sometimes you have the model, and it also tells you which paper it's from. You can export the data as a tab-separated variable file or a comma-separated variable file. SNaX has a very powerful, SNaX has a very powerful graphical interface. So you can plot the data also in any way you want. So you can customize the plots completely. You can customize them according to the size, according to the axes. You can have the legend customized, how many columns you want, where you want it anyway. You can customize, of course, all the titles and stuff. And once you're fully satisfied with your customized plot, you can download it. As I mentioned before, one of the things is that the light curves can be assumed to be going as a power law with time. You can actually fit this power law with time on the data plots itself. So you can just stick this value, and it'll give you the power law index for all the graphs that you have there. So for every supernova data point that you have there, I mean, every supernova light curve, you can get the power law index. And finally, as I said, you can download them. You can also recalculate all the data to 0.3 to 8 keV. Now, all this would not be very useful unless you could upload your own data, of course. You can easily do that, and that's the whole thing which makes this a very powerful database, just like many other optical databases. So you can upload your data. This is done by a CSV spreadsheet. There's an example template file given for your reference. You can just look at it, but most of the columns are self-evident, just giving all the data about the supernova and then giving all the X-ray data from various different things. Most of it is either from Chandra or XMM. A lot of the new one is from Chandra because it has much better spatial resolution. So you can upload your data, and I would really ask you to upload your own data because that's something that's really missing. A lot of people send me their data files or their papers and tell me to upload it, which kind of misses the point. So finally, please use the database, freely download and upload your X-ray data, and please do upload it. It is a moderated database in the sense that we only include published data. We cannot include unpublished data. And finally, if you do use it, please cite the papers that I described earlier. This gives us an idea of how many people are using it. I know people are using it, but not citing it. And this helps us to continue to maintain it. So I hope it's very useful to people in the X-ray field. And I hope that more and more people will use it. And I will leave my email address here. If you want to send me any questions, you can also put them on Slack, and I will answer any questions. Thanks very much. Thanks.
Thank you. Thank you for this advertisement of the database. It's very nice to have that here. And we don't have time for questions, but please send questions on Slack, and we'll monitor them. That's a good place to have a discussion. Thank you. And our next talk is the contributed talk by Claudia Comito from Jülich Supercomputing Center. And it will be a talk on parallel and scalable data analytics with heat. Claudia, can you
Thank you so much. Yes, I'm sharing. Does that work? And
yes.
Yes. Does it work well? Okay, thank you so much. Thank you so much for having me. Participating in an X-ray astronomy is really a first for me. A bit of background, a bit of context. My background is in submillimeter astronomy. I was a calibration scientist for the Herschel Space Observatory for basically the whole mission, and actually switched to scientific computing. Hang on. I switched to scientific computing pretty late, about 15 years after my PhD, in fact. So I really enjoyed the earlier session with David and Christina. But anyway, so in 2018, I joined the Jülich Supercomputing Center to work on a large cross-discipline project in applied science. And by that, I mean all kind of applied science, I'll tell you later. And this library I'm going to tell you about today is basically part of what came out of this project. So what doesn't work now? Yes. I'm going to give you a bit of a background and tell you a few words about its programming model, and then the two legs that it really stands on, the low-level operations part, that's more like the NumPy-like distributed NumPy part, and the high-level algorithms, it's more like the scikit-learn, machine learning part of the library. I'm going to say a few words about how you might want to proceed when heatifying your code, if you so wish, and a few words about what's coming up in the next months and hopefully years. But enough with that. Okay, let me take a step back and address now the basic of what we are trying to do with it. This slide is really a very large oversimplification, so please allow me that. But let's say that in research, there are two somewhat different layers or two different classes of problems that we now label data science. So number one, and here's the oversimplification, we have large data sets about underdetermined systems. We model the many variables that describe our system, and in order to get statistically significant results, we explore very large parameter spaces, and most of you are way more proficient in multivariate analysis than I, so I'm not going to go on, but the point here is these are very computationally intensive tasks that we seek to speed up, not because there aren't enough years in our PhD studies, but also because there aren't enough years in our career to achieve the knowledge that we are seeking. And we usually trying to speed up these calculations by optimizing algorithms, as we just heard. One example, and also by parallelizing the calculations. So I have to note here, when we usually say about parallelizing our calculations, we are talking about what computer scientists call embarrassingly parallel calculations. So these are the tasks that run independently from each other anyway, and you can load them on different nodes and run the calculations independently on different nodes, independently from each other. The nodes or the processors, however you want to call them, don't need to talk to each other at all. So then there is a second layer of complication that is actually more and more a feature of large scientific projects. That's exemplified by the dreaded memory error in NumPy. So that's something that happens when the data you're trying to load are so large that they don't fit in your single node memory in your CPU. Or you can load your NumPy arrays, but you cannot perform the operations you need to perform on them before being able to chunk the data up for your parallel calculations. So this side of the problem is where our use cases are coming from. So they need memory distributed computing in order to perform the research, and that means they must be able to use the entire memory of the available architecture. But when you do that, that means that within your algorithms and really within every single operations, you need to organize the communication, the synchronization among processors. And this communication part is hard, I found out. So most scientists have no training in parallel computing, and this is the challenge we wanted to address when we started developing HEAT. We wanted to provide a tool for scientists to easily parallelize their computations, whether they were embarrassingly parallel tasks or not. So yes, I have a bit of a heads up here before your attention slips. I know it's attention span is short. I'll mention this at the end of the talk again, but we are putting a big cross-discipline funding proposal for further development of our data analytics. So if at the end of this talk you think HEAT could help your large projects, but needs to be expanded for that, and you want to collaborate on this, and it helps if some of you is based in the EU, of course, please get in touch. All right. Okay, so we have a cross-discipline project. As I told you, our use cases are from neuroscience, aerospace, biology, earth science, I think, and 2 or 3 more, no astronomy so far. And what we wanted to do with this big project was to distill, let's say, and then provide general methods and the general toolkit for data analytics, especially big data analytics in science. So this, of course, includes machine learning and neural networks. But not only, you still need to do your linear algebra, you need to do your distributed statistics and so on. So our target audience are SciPy NumPy users, as I mentioned already, and HEAT's goal is to help these users, these scientists, overcome their single node memory bottlenecks and parallelize their calculations without having to become experts in parallel computing. Okay, just a few words now about the library itself. Heat is an open source Python library. It's based on PyTorch, which allows us the eager execution paradigm approach that we so much enjoy in NumPy and SciPy, and so much miss, at least I, in TensorFlow, for example. It offers multi-node support via message passing interface and multi-GPU support as well. And well, the parallelization of the operations and the algorithms is basically under the hood. You don't need to worry about that. I'm going to show you an example or two later. So now, this is just a quick example to show you how similar using heat is to using NumPy. In this case, I'm just defining a not so big data cube. And by the way, heat's data objects are called DND arrays, as distributed ND arrays. So this is a sketch I'm going to show you in a second on 3 processes. But anyway, you can see already there is one difference with NumPy. That's the split attribute to the array, to the data object. This basically enables data distribution. So it tells heat along which dimension the data should be distributed. A bit more visual example of this is like this is the data cube, and if you set split to 0, the data will be distributed across your, in this case, 3 available processes along the 0 dimension, and which is the Z dimension if you are thinking in X, Y, Z. And if you set split to 1, the data will be distributed along the rows. And if you set split to 2, the data will be distributed along the columns in this case. You can also not set the split attribute, or it will be set to none, and then you have a copy basically of your data on each process. All right, so a couple of words about the programming model. This kind of standard parallel programming model is the bulk synchronous model, where you distribute your data and you start the calculations, and the calculations happen independently on each process. In this case, I have 4. I'm not sure why, but anyway. And then in the bulk synchronous parallel model, synchronization, data synchronization among the ranks, among the processes happens at given times. And we have introduced a bit of asynchronousness in this, in the sense that whenever we assess that within an operation or within an algorithm, communication needs to happen, either between 2 processes or collective communication, then the communication happens right away, and the transferred data are immediately available on the receiving rank. They're immediately available for follow-up calculations. So on each process, so we call it the process local data object, is their PyTorch tensors, which means that the process local operations are also PyTorch operations. That helps a lot if we want to be fast, at least as fast as NumPy in a 1 node scenario. So the communication, as I mentioned, happens via message passing interface, and MPI for Pi provides the bindings. Yes. So let me talk now about the low-level operations. That's one of the 2 legs I mentioned earlier. We follow pretty religiously the NumPy API. Our guiding light is that you should be able to import heat as NP, and your code should run apart from the memory errors, I suppose, if you have very large data. But within this low-level operations part of the library, we implement distributed linear algebra, distributed reduction operations, distributed binary operations, manipulations, statistics, right? Whatever you need for your, let's say, more basic calculations. We have parallel I/O and GPU support thanks to PyTorch. The only thing you need to have your calculations run on the GPU is to set the device attribute when you declare your data. Yes, just an example. Again, I'm now loading some array from a file or from a NumPy array or from a tensor. That's how you define it as a D&D array, as a heat array. In this case, I'm not specifying the split attribute, so the data are basically copied on every process. But this is not what you want to use heat for, so let's go on and distribute our data. Now I have X and Y. In this case, in my imagination, at least in this sketch, they are two-dimensional matrices, and I am distributing X along the rows. I'm distributing Y along the columns. And then, as you can see, basically each rank or each process only loads a slice of a predefined slice of the data. So I distributed this data along these directions, 0 and 1, because I knew I wanted to run a dot product on these two matrices. And that's a more convenient way of doing it. So from the point of view of the user, you can just run the dot product on these two distributed ND or distributed arrays. As you would do with NumPy, you wouldn't have to worry about what's going on in the background. But of course, in the background, there is some communication that's happening in order for Z to be then a distributed dot product. And one thing I want to bring up again is that all these arrays, let's say a D&D array is not just a collection of independent data slices on your processes. It is a single entity. So whatever follow-up heat operation you want to run on these D&D arrays, it will also be a distributed operation. We have reduction operations, as I mentioned. We have really a lot of what we call low-level NumPy operations that are not exactly straightforward to parallelize. They're not embarrassingly parallel, let's say. So yes. Then let's go to the high-level algorithms. This is more like the machine learning part. It's both the operations and the algorithms are optimized for high-performance computing. So we do worry that the operations are scalable. It's not always the case, but we certainly pay a lot of attention to that. So by now we have a few clustering and classification algorithms like k-means, k-nearest neighbors, lasso regression, and a few more spectral clustering, I think. The machine learning part of heat follows the same API as scikit-learn. So that basically if you have your scikit-learn code and the algorithm you're using has been implemented in heat, then you should be able to just port your scikit-learn code into heat very easily. And the only thing you have to specify again is the data distribution attribute. I hope you don't hear. Yeah, okay. All right. So we also have a data parallel neural networks part that if you're using PyTorch and for your data parallel neural network training, it might help you to speed things up quite a bit. I have no time to go into that. And yeah, let me go on. I also have no time to go into the details of our performance, but you can check out our paper. There is a big discussion on that. We, at least in the 2020 version of our benchmarks, we significantly achieve a significant speed up with respect to Dask and CuPy. As I said, the benchmarks, they are available on our GitHub repo, and they are from 2020. And in this year, we have worked a lot on speeding things up. So I think they might look even different, or I mean, better for us after a year. A few tips on heatifying your code if you are so inclined. I mean, there would be the brute force option would be to import heat as NumPy and see what happens to your NumPy code. You will most likely run very quickly into functions that are not available on heat. They're not being implemented yet. They've not been implemented yet, either because nobody asked for them or because they're a bit more complicated to implement in a distributed fashion, or in a parallel fashion. So please, anyway, bring up your requests, your feature requests. We really rely on the community to let us know what they need. And then another piece of advice I can give you is to double check your data types, because we expect our users to run their calculations on GPUs a lot more than NumPy users. Well, let's say totally more. And we then default to 32-bit more often than NumPy, let's say. Yes, so we had, I think I can leave this on, just head to GitHub for issues and feature requests, and I'm looking forward to hearing from you.
Thank you. We have time for questions, if there are any. I have one, actually. So if I want to use heat in my calculations, do I just load heat and then the data and just run my code, or I have to do something in my code? Or pp install, yes, but
sorry,
do I have to do?
I forgot the last click. So yes, well, you use it just as any Python library. So you would install heat, first of all, if you want to use the MPI, which I suppose you do, the multi-node capabilities. You also need to install MPI for Pi. Right. And then you go through your NumPy code and try to replace as many NumPy functions as possible with the heat functions. The syntax, the API should be exactly the same in most cases. And then maybe I can write it down. A heat piece of code really doesn't know whether it's running on a cluster or on your laptop. The only thing you need to do is when you run your code, you use, I use OpenMP, so OpenMPI, so MPI run, and then the number of nodes that you want to use, the number of processes. Some other people use MPI exec as a command, but actually I can write this down maybe in the Slack if it helps.
Yeah.
So what you would call this piece of code with MPI run.
Yeah. Okay. All right. Yeah, we'll try. Well, I'll try and see. It looks good. So there's no questions here, but I encourage everybody to go on Slack and have discussion on Slack. And we thank you, Claudia, for this good introduction to parallel programming.
Thank you so much.
Thank you.
Thanks for having me.
Thank you. Oh, there it is. That's the Jülich Supercomputing Center. Thanks.
Yes. Thanks.
Okay, so our next talk is by Vinay Kashyap. Let me see, where is it? Yes, so it's by Vinay Kashyap from Chandra X-ray Center, and this is the lightning talk on upper limits to the X-ray flux from Betelgeuse. Okay, Vinay, 5 minutes.
Thanks, Anita, Rudy. My name is Vinay Kashyap. I'll be talking about X-ray observations of Betelgeuse. You all may have heard of this great dimming of Betelgeuse that took place from late 2019 to around mid-2020. What you're seeing here is the ALSO amateur astronomers variable star observers, light curves collected from all over the world. Observations made by amateurs, and you can see that there's this massive dip that happened in late 2019, and it set off a massive media frenzy. Whether it was going to go super or whatnot. We know that it wasn't going to go supernova. It still got many tens of thousands, if not hundreds of thousands of years of life. But we did wonder if there's large mass flows happening. Surely there must be shocks and collisions that perhaps could be visible in X-rays. So we asked for Chandra director's discretionary time observations. And Chandra did observe Betelgeuse with the HRCI for 5 kiloseconds. Once at the minimum of the optical and once after it recovered. And these are the vertical bars that are plotted on this light curve. And not to keep you in suspense, no signal was seen. Of course, just because there's no signal doesn't mean that you stop working on it. What that means is that we have to put upper limits on it. When I say upper limits, I have to be clear about what we mean. I mean that it's the intensity of the brightest source that would still remain undetected, or conversely, the intensity of the dimmest source that would be just barely detected. And I want to, there's a lot of confusion about what exactly upper limits is. And I wanted to sort of emphasize that I'm not talking about the upper uncertainty bound on the estimated source intensity. If you want to get information about that, there's a lot of work that's been done, starting from Tom Loretto, 1992. But what I'm going to talk about when I say upper limits is dealing with sensor data, something that does not exist. And there is a whole lot of other work that's been, papers that have been written on this, starting from Erik Feigelson and his students way back in 1986. You'll notice that there's one paper here that's appears in both lists because they tried to do a combination, a very clever way of combining the two, which I can discuss later on Slack if needed. So what is the thing? So what is the thing that you're dealing with when you're talking about upper limits? So first of all, there is a, suppose there's a background and you're willing to accept that there is a certain false positive rate that you set by setting the threshold. Anything above this, to the right of this line, you'll accept as a false positive. Anything to the left, you'll accept as a true negative. When you add a source, this is the original no source case. When you add a source, this distribution moves to the right, and you start seeing more instances beyond the threshold. As you push the source intensity higher, you're going to see more and more of these true positives and fewer of these false negatives. Now, there is a you have to now say what you're willing to accept as the false negative when you say there is a source is barely detected, and we usually choose this value of beta, which is also the power of the statistical power of around 50%. So we report the count rate detectable at 3 sigma detection 50% of the time. That's beta f 0.5. And from the February 17, 2020, the minimum of the optical thing, we found a count rate of around one-ish count per kilosecond. After recovery, it didn't change much, around 1 count per kilosecond. Combined, dropped around 0.6 counts per kilosecond. You can convert that to an actual, physically meaningful units, like, this is X-ray luminosity for a given, on the left, it's a thermal model, on the right, it's a power law. This is Lx by elbow. And you can see, for instance, that if your model assumes that there's if you're expecting an Lx by elbow of 10 to the minus 6, then anything to the left of this is forbidden from this analysis. That's my summary. Thank you very much.
Thank you, Vinay. Very nice simulations, and hopefully people will have a discussion and comments on Slack. We don't have.
I joined Slack, so I'm happy to answer.
Okay, very good. Thank you very much, and we'll have to move to our final talk for this session. This will be the invited talk by Erik Feigelson. And Erik Feigelson is a professor at Penn State University. He is well-known advocate for astrostatistics, and his contributions to astrostatistics started long time ago and are well known. So we are really happy to have Erik giving his invited talk today. And he will talk about statistical approaches to detecting X-ray variability. Okay, Erik.
Thank you very much, Annetta. It's a pleasure to be here. Okay, so I'm going to be talking about how one can detect X-ray variability and with different statistical approaches. This is work with Vinay Kashyap, who you just met, and Annetta Smith-Gaska, who you also just met. So it's a pleasure to have my colleagues here. My entire talk is going to be based on this data set. Okay, it's 312 photons from a variable star observed. It's a pre-main sequence star in a star-forming region, and you can see this is the data that I'm going to consider is photon arrival times, and here's the energies of each photon as well. And you can see here that around sort of a fourth the way through the data set, there seems to be a concentration of photons. Okay, so we're going to study this. So here is the univariate time series that is binned into basically 1 kilosecond bins. And you can see that it's very weak, maybe even consistent with background here. And then there's a flare, and then it seems to be elevated after the flare. So these are nicknamed superflares, and they're studied for various reasons: the effect of the X-rays on the protoplanetary disks and on the young planetary atmospheres around them. It's astrophysically interesting as well as a statistical problem. Okay, so what might an X-ray astronomer say? Well, they might say, well, is this source constant or variable? Just is it a variable source? And then if it is variable, could we characterize it? And we sort of view things as both flare-like, sort of, an event, or some sort of a continuous process with trends, or maybe with autoregressive behaviors. A statistician considers the same questions, but they have a different language. They would say we will do a test for inhomogeneity of a Poisson process. For this flare-like approach, we would do a change point analysis. And for the continuous behavior, there's both smoothing, which I'll ignore, but also autoregressive analysis or modeling. So this first one is a hypothesis test, where one does not seek any parameters, one just wants a probability, whether or not it is homogeneous or not. And here one would actually construct models, parametric models, and seek parameters. For instance, what's the time of the change point, if it exists? Okay. So my talk is limited. I'm only going to talk about the statistician's perspective. There's a lot of good stuff about what X-ray astronomers do, but I just don't have time. And then sort of oddly, I'm not going to talk about Python. I'm going to talk about R. So R is the statistical software environment developed by statisticians for everyone. It has, no one even knows how many functions, how many procedures in it, maybe well over 100,000 in 18,000 packages. And what you'll do is that you'll see in the bottom right hand of my slides, you'll see the name of a CRAN package, and you'll see that roughly a dozen CRAN packages seem relevant to this problem of detecting and characterizing variability in a faint point process. This talk also is going to appear in written form, somewhat enlarged, in a gigantic 4-volume handbook being prepared by Springer right now. That will probably take a couple of years to come out. I was sort of a little irritated that this particular question, which is so clear to high-energy astrophysicists, doesn't have a single place in the statistical literature where it's just presented. So I can't point to a single book or a single package from which we can tap the statistical methods. So here are just some ideas. Just a textbook and stochastic processes are quite useful. This is a slim volume of Poisson processes by a distinguished British mathematician. It's a fascinating book. It's almost like you could read it like a novel almost, rather than presenting methodology. This is the current leading textbook on sequential analysis for change point detection. The original book was written in the 1940s, I think, by Abraham Wald. This is an elementary textbook by Joe Hilby, who, by the way, was a an astrostatistician. He recently passed away. And then I have some more advanced or narrow books that may or may not be useful. So I can't really point to any one of these as perfect for this problem. So the outline of my talk that we've been thinking about is to first look at some unbinned actual photon arrival times, non-parametric tests for variability. Then we will consider binning them. We're not binning them to get Gaussianity, we're just binning them to get an evenly spaced time series. Bizarrely, we can actually consider the question without looking at the times, and then we can look at the temporal information. Then we'll get to some parametric change point models and end up with a more complex one. These asterisks represent this. The title of this conference is novel methods. So most of what I'm going to talk about are not novel. They're just sort of in the statistical literature. But this one is going to be has just only been presented for astronomers very recently by Costa Getman and myself. And this one is a new procedure developed by Kong Chu and his colleagues, including Vinay Kashyap and others who may be in this conference or watching right now. Okay, let's start the talk. Let's see how we might do it. Well, the first thing you might do is to say, okay, thank you very much. We have 312 arrival times. Let's do a Kolmogorov-Smirnov test with compared to one sample test to a model of a constant flux. And there's the model, is the dashed line. Here is the cumulative distribution function of the arrival times. And the KS test gives a probability of 4%. That's not very sensitive. Okay, that's because it's a short-lived event, and the KS test is better at saying, let's say, it's sort of faster in the first half and slower in the second half. It would be more sensitive. So this is a case, a rather extreme case, where one should do a different CDF test. So the Anderson-Darling test is the most sensitive, and it gives, you can see, far more sensitive a detection of the hypothesis of whether or not there's variability. In general, astronomers should stop using the KS test and use the Anderson-Darling test. I don't know any situation where KS is more sensitive, and this is a good case where it's not sensitive, and you would miss the detection of variability. Okay, there's a classic field of statistics for industrial quality control from the 1950s and 60s, and the Q-sum test is classic. What it does is that it measures the maximal difference between the sample means before and after each data point. Okay, so you go to a data point, ask what's the mean before and the mean after, and you compare those. So it ends up, it's highly sensitive to the flare. Okay, the probability of seeing variability is very high, but it completely misses when the flare occurs. It's just not designed for that, or it just does a bad job. Again, it's designed for behaviors where the behavior is the same in the first part and then changes in the second part. So what we're seeing here, these are classic non-parametric tests, unbinned, which have very different performances. They actually do different things and look for different things. And that's sort of interesting. That's sort of a theme of my talk, is that there isn't a single answer to the question, how do we detect variability? There are different statistics that do different things. Okay, now let's bin the data, and I just chose 1 kilosecond bins, where so it's a Poisson process with about two counts per bin. Okay, I just chose that. The purpose of the binning is not to get Gaussianity. The purpose is to get an evenly spaced a sequence of measurements, in this case, count data in evenly spaced, because there's a whole lot of statistics that are designed for evenly spaced time series. So we have evenly spaced but Poisson distributed count data. Okay, so what can we learn from this kind of thing? Well, now let's not even use the temporal information, but just ask how many of the bins have 0 or 1 or 2 or 3 or 4, whatever, counts, and one of them has 12 counts. Okay. And we can just ask, well, is this distribution consistent with a homogeneous Poisson process? And there it is, that the green curve is the prediction of a homogeneous process. And the answer is no, it's not consistent at all. There's too many zeros and too many 12s, and it's just the wrong shape. So there actually is a classic chi-square test for this, and it's highly sensitive that the count distribution is inconsistent with a constant Poisson process. Another way of phrasing it is that a homogeneous Poisson process, the variance and the mean should be the same. So the variance should have been 2 with the mean of 2, but in fact the variance is 3.7. And this is called over-dispersion. So this is a hypothesis test for an over-dispersed Poisson process. This is all described in Hilby's book. We can also ask a different question, which I'm not sure I like this one very much. Okay, we can say, well, just you see that 12 point there, just look at that single bin. Is that consistent with a homogeneous Poisson process? And so the answer is it's inconsistent at the 0.1 percentile level. The reason I don't like this is that we have to do a correction for multiple hypothesis testing, and I've chosen the conservative Bonferroni family-wise correction, but I could have chosen another correction, sort of what Vinay was just talking about, where he looked at alpha and beta. It's sort of a false negative question. So I don't particularly recommend this test, but it can be done, and it did detect variability, but not as sensitive as the over-dispersion test. By the way, I'm going to change my topic for just a moment. Remember, I have a bivariate data set with energy, and I can ask in the binned data of the count data, I have a covariate, which is energy. Is there a, in this case, linear relationship between the counts in the bins and the energy of those counts? And the answer is the generalized linear model slope is not significant. There's no significant relationship between the variables in the sample. And this is called a Poisson regression. It's performed by maximum likelihood estimation. And it's an example of GLM, generalized linear modeling. Okay. So there's no evidence the energies depend on the variable fluxes. Okay, let's go back to the question of variability, and let's actually use the temporal information. And I'm going to start with a very primitive one, dating back again to the 1940s, that evaluates a randomness of a sequence of zeros and ones. So what we do is we take the number of counts in each bin and subtract the median from it, and just say it's 0 if it's below and 1 if it's above, and so is there a lot of like 0 1 0 0 0 1 1 1 1 1 1 0 0? There's a whole string of ones. Then the Wald-Wolfowitz runs test will sort of detect that. So it ends up it's not very sensitive. It really accepts the constant flux model, and the reason is that the runs test assumes a stationary process, that the interesting behavior occurs over the entire data set. Whereas, as we saw, the interesting behavior seems to be concentrated in a narrow thing. And we're going to see this repeatedly in my talk, that some tests are designed for detecting stationarity, detecting variability that is stationary. It means that whatever the variable behavior, it occurs everywhere. And others are really designed for finding events, okay, that have change points. So it ends up the runs test was pretty lousy for this particular case, but it might be better in some other case. Okay, so let's now use the temporal information. We're still using the bin data, and simply look for autocorrelation. This is the premier tool for a non-parametric examination of correlation in a data set, and this is in in an evenly spaced time series. And so we're going to look at short lags. Actually, we've got quite a number of lags here. And we find that, yes, at short lags of 1, 2, 3, 4, 5, 6, 7 lags, bins, there seems to be a strong up to 50% autocorrelation for the test here. And so this looks definitely like a detection. The problem is that the mathematics for autocorrelation functions, at least the mathematics that I've been able to find, there's maybe some papers I just don't know about. Anyone who knows, please let me know whether they're good for Poisson. The problem is that these probabilities, that's the 95% confidence level, that's based on Gaussian data. And they're probably elevated for Poisson data. So these things, the tests associated for this are called the Durbin-Watson test and the Lejeune-Box test, which is the portmanteau test, which is really good. But I don't think the probabilities of the Lejeune-Box test are right for Poisson data. I'm not sure. Any statisticians in the room, any help, let me know. So I didn't actually use this one so much. Okay, so another one is to model it, do a parametric model, and the most common parametric models that assume stationarity is for autocorrelated behaviors is to run let's say a linear autoregressive model. And these are of a broad class called ARMA, autoregressive moving average, but there's a whole lot of them. There's ARMA and ARIMA and GARCH, and this goes on, there's dozens of them. We're going to be looking at the INAR and PAR models. These are the ones where the data are integer counts, okay? And so there actually are autoregressive models that are designed for this data set. So here I fit, here's my code. This is the CRAN package where I found in R, where I found the code. That's why I did no coding for this talk. It's all within R. I spent a lot of time looking around in R. There's so many different possibilities, but I didn't write any code other than a script that implemented them. I ran an INAR1. It's very similar to AR1. You may have heard of CAR1 for irregularly spaced data. It's a very simple linear model. And I didn't expect it to work because it assumes that the variations are the same everywhere. So this is a maximum likelihood estimator, and there's only one parameter, which is the coefficient of the first autoregressive in our parameter. And to my shock and amazement, it worked very well. So it had a model, which I'm not showing here. These are the residuals to the model. This is the autocorrelation of the residuals of the model, which is absolutely consistent with white noise. It's not Gaussian white noise, it's Poisson white noise, but it's white. And I couldn't believe that a model designed for stationary behavior, that all 150 kiloseconds are all the same phenomenon, could account for this gigantic bump there at 40 kiloseconds. Just blew my mind. So scientifically, this is sort of interesting. It means that even though almost all of us would view this as a flare-like phenomenon, it actually can be well modeled as a continuous process as well. And it ends up in the literature of flaring from stars like this, X-ray flaring, is something called the avalanche model. It's developed for solar flare occurrence rates. And that is an autoregressive stochastic process. It's most recently for the sun. They've used an ARFEMA model, which is a nonlinear extension to the typical ARIMA model. But the point is that if I were a scientist, I have to recognize that both inhomogeneous, non-stationary inhomogeneous models, like with flares, apply, and a continuous stationary model applies. And that was quite surprising to me because it doesn't look very stationary to me. So that was that was my biggest surprise in preparing this talk. Okay, let's now go to the parametric modeling of flares. Okay, change point modeling. Okay, so now we're no longer doing autoregressive stochastic modeling. We're doing deterministic modeling, And we're going to take the same assumption that Jeff Scargill has famously and effectively used in X-ray and gamma ray astronomy for years now, that he calls Bayesian blocks. But the statistical model is a piecewise discontinuous levels of several levels. And the point is to find if there is a change, where the time change points occur, what times they occur, and what the new levels are. Okay. It ends up, this is quite a challenging statistical problem. Okay. Jeff deserves tremendous credit for basically solving it. He uses an advanced computational method called dynamic programming. And the problem was also addressed in statistics, also in the last 15 years, roughly, by Chib and others, using a completely different algorithmic approach involving latent variables. Okay, so this is the Chib approach, and there's actually a code here in called MC Poisson change. That's a function that actually calculates this directly. And here's the solution for this problem here in the 1 kilosecond bins. That there's two change points. This is the time and the statistical distribution of the first change point. This is the time and statistical distribution of the second one. It's a little asymmetrical. You got to decide exactly where you want to put the second one. That's interesting. That's because that's a little asymmetrical and coming down. And these are the probabilities of the three components, the first, second, and third. And these are the levels, 0.8, 5.6, and 1.8 X-ray counts per bit. So there we go. This is very similar to Bayesian blocks, but happens to be different. This is the one that we implement in Gitman and Feigelson, where we had a very large data set and with thousands of these light curves that we were looking for flares. Okay, so that's very nice to see that. On the next couple of slides, I'm going to go pretty quick because it's sort of a little weird. These are rather narrow, sort of disciplinary specific methods that are not widely used in statistics. This one here in a JASA, Journal of the American Statistical Society paper some years ago, simultaneously fitting an ARMA behavior with non-stationary outliers. And they have two different kinds of outliers called additive outliers and temporary outliers, temporary changes. And here it is. This is the additive one. And the additive one found boom, boom, but also found changes here and here, which don't really look right. But the temporary one did a really nice job here. I haven't studied this method, but just want to say that, oh, okay, maybe this Chen and Liu method might be useful to X-ray astronomers. I'm not sure. Sort of interesting. And then here's one.
3 minutes.
Thank you. And then here's one from epidemiology, and I won't go into it, but it did a pretty bad job detecting outbreaks of diseases. So it could be applied to X-ray data too. Okay. My last one is a very interesting paper that has just emerged, and it actually deals with the more challenging issue that's related to the eBASCS paper that we just heard from Antoine Meyer a few minutes ago, which is going to deal with four-dimensional Poisson process. So this is right ascension declination and time, and then the color here represents energy. So it's actually four-dimensional. And our particular source is, I think, this blue stripe there, that's sort of faint in the beginning, and it changes. So this is now, here it is. Here's the paper. Hans Gunther and Vinay Kashyap are in the room here, are part of this conference, and they developed with their colleague Kong Chu. Change point detection, image segmentation for astrophysical images. Okay, so this one again, as with Bayesian blocks, it's a piecewise constant flux model, but the model selection is not based on AIC or BIC. It's based on the MDL criterion, which is interestingly new. The algorithm is quite computationally intensive and requires sort of doing a lot of stuff ahead of time to get it to work. But the code is widely available. It's very general, because it can find change points in space, that's sources, time, that's flares, and energy as well. So here's the four examples of what it found in that data cube. This was the most variable source. This was our variable source. Here is a very faint variable source. And finally, here's a very bright constant source. So it's a very broad approach to this kind of situation in X-ray astronomy and gamma ray astronomy. So in conclusion, I'd like to say that there's actually a wide variety of methods to detect and characterize variability in low count X-ray and gamma ray sources. Most of these methods are not being used by X-ray astronomers. And here's the four categories. That was my outline at the beginning. Each method is sort of different. They sort of oriented towards detecting and sensitivity in different ways. Some are from classical statistics from the 1930s and 40s. Some are sort of focused parametric models from Poisson stochastic processes. And then a couple of them are being developed right now by astrostatistical collaborations today. And like the last comment is a criticism that the major software packages available to American X-ray astronomers like Chow and Kronos are really inadequate. They basically do almost none of this. That the codes are mostly available in R, and these can all be wrapped into Python. Okay. Thank you.
Thank you, Eric, for this very interesting summary of the issues with variability and Poisson processes. We have time for questions, and I will start with the question and comment from Jeff Scargill. You can see, Eric, the question when you click Q&A at the bottom of the Zoom. So Jeff asks or says, in practice, all sources are variable at some level, not just due to photon counting fluctuations. The question should perhaps be how variable, not is it variable?
Yes.
And then how do you interpret it?
Jeff, I can answer quickly. Whether it's a good answer, I'm not sure. But my answer to this, my thinking is that first people should be doing hypothesis tests. And if it looks like it's sufficiently probable that there is variability, then they should ask what's the parameter, such as what's the amplitude of variability. So I would first do a hypothesis test, or a bunch of them, and then I would do parametric modeling. And really, for instance, the paper by Kashyap et al. 2010, and earlier papers like Feldman-Cousins, the Kashyap paper is really nice in distinguishing between the existence of variability and the estimation of the values of the variation. And there's just one's non-parametric and one's parametric. Do first one and then the other.
Yeah. So,
do you agree, Jeff?
Yeah, I can let Jeff talk. Actually, I realized that. Jeff, can you talk?
Yeah, I can talk. I don't know if you can hear me.
Yes, I can.
Yes.
Well, she didn't read the last sentence of my question. So how do you interpret the results and of a yes/no test? And you sort of answered that, but really the point is it variable? Really should be a more complicated question. Is it variable in such and such a way? I mean, you did a good job of outlining that there are various ways that the variability can occur. And I love the distinction between single flares and continuing stochastic activity, and that's a key thing. But I'm just pointing out that a yes, no, is it variable or not is a very rudimentary question that really can't be made very meaningful, in my opinion. You have to add more stuff to the question to make it meaningful. How much and what sort of variability?
Yeah. Perhaps I'm just biased by the way that I do my science. When I look at 1,000 or 10,000 X-ray sources, a whole lot of them are constant. I just go through and 90% of them are not variable in that data set. And thank you very much. I won't think about those anymore. And then I think about the 10% that satisfy the one of the hypothesis tests.
Okay, so then you're sort of sweeping under the rug the fact that they are all variable at some level. You just haven't detected it.
It's not in my data set. It's not. I don't have a long enough exposure. I don't have a sensitive enough telescope. Or my background's too high. There's a lot of reasons I won't detect.
No, I'm being very, very picky, but this integer autoregressive model is new to me. That's really interesting. I'll have to check that out.
That's cool.
Yeah.
X-ray astronomers should be aware of it, and when they want to, try it out.
Right.
Thanks, Eric.
Pleasure.
Yeah, thank you for this nice commentary. It's actually nice to be able to talk instead of me reading questions.
I've put a link to my slides on the Slack a few lines up.
Right, we'll do that. And oh, that's my phone beeping on me. So I think I don't see any more questions. And if there are questions, please put them on Slack. Thank you, Eric, for a very nice talk and presentation. And I'd like to thank all the speakers from this session for very interesting and talks and things and you can consider in the future for us. So thank you very much, and we will take a break and meet tomorrow morning for the next day of workshops. Thank you, everybody.
Thank you, Annetta, for chairing.
Thanks, Rudy.